So hello everyone, welcome back to our YouTube channel. Today we are moving forward with our Verilog series, and the topic of the day is operators in Verilog. In the last video, we discussed about what are all the various data types available in Verilog, and the two main data types which we need to focus on: wire and reg. Today we will be taking a look at the elementary operators that are available in Verilog. My plan is to start with all the required operators as a basic data so that you can start practicing as the series progress and all the complex operators like replication operator, part system operator, we will be covering those in later videos. So after today's video, I will give you an assignment that you all need to finish. Now let's begin today's video. The first kind of operator there are available in Verilog are logical operators. Now, so most of you should be familiar with programming in C language. The operators that are available in Verilog are more or less similar to the operators that are available in C. And wherever there are differences, I will mention those. So what are logical operators? Logical operators simply help us to perform any logical operation with any kind of variable we have in Verilog. Now, take a look at this module. I have a register A, B. I have provided some value. Register A is equal to 1, register B is equal to 0. Then I have register X. Now, for now, ignore that 3 down to 0. It's just specifying what is the width of register. By default, each and every data type in Verilog is of single bit. For multi-bit, to use multi-bit data type, we need to declare it like this, 3 down to 0. So it's a 4-bit data type. In the next video, we will also be taking a look at what is this called. This is how a width defined. This is a vector, and what a difference in vector and arrays. That will be our next topic. For now, just keep in mind that by default, each and every reg and wire are just single bit. So X is a 4-bit, Y similarly a 4-bit, while A and B are single bits. Then I declare wire not A and AB or AB equals XY not equals XY. Here, I am just assigning not of A is equal to not of A. The logical negation operator helps us to invert the value of A. Then there's logical AND operator, which takes the logical AND between two values, A and B. Logical OR operator, logical equality, and logical inequality. Most of you can guess the answer that here A is 1, so not of A should be 0. A is 1, B is 0. So output of AND AB should be 0. A is 1 while B is 0. So output should be A. X equal to Y. So are both X and Y equal? Yes, they are equal. So this should be 1 is not of X and Y. Yes, they are equal. So not of X and Y. The output should be 0. Now you might think what is this assign keyword? As we have discussed earlier, wire type variables need to be driven continuously. Hence, the assign keyword is used to make sure that any wire type variable is driven continuously. This is a keyword provider variable which is used to assign any value to wire type data. The summary, as we discussed earlier, not of a the logical negation, true becomes false and false becomes true. And is true only if both the operands are 1, or is true only if any one operand is true, any one of the operand is true, while equality operator matches only if all the bits are matching, and no difference operator that inequality is false. Now they are bitwise operator. Earlier we had logical AND and logical OR. Now we have bitwise AND, bitwise OR, bitwise negation. So how are these different from logical operators? Logical operators consider the whole values as 1 or 0. That is, any non-zero value. If A and B were multi-bit, like if instead of A and B I took here X and Y, then any non-zero value it's considered as true in logical case. That this will be 1 and this will also be 1. If I had X and Y here. But in bitwise operator, each bit is treated separately. So in bitwise negation, what output I will be having? Each bit of the variable that I am applying the negation operator on it will be flipped. Bitwise AND bitwise AND takes AND of each bit of the two variables. Same for bitwise OR, it compares each bit bitwise, then provides the output. Now, what is bitwise exclusive OR and bitwise XNOR? They are they also work similarly like AND or not. The XOR operation is performed bitwise on the both bits. See what should be the result of all this operation. We had the value of A assigned as 1, 1, 0, 0. So not of A should be 0, 0, 1, 1. This here, as we mentioned earlier, negation operator just flips all the bit. So bitwise operator will flip each and every bit. And for AND we compare each bit. If both of the bits are 1, only then the result will be 1. So LSB of both it's not 1, so 0, 0 and 1, again 0, 1 and 0, again 0. Finally, both MSB are 1, hence output is 1. For OR, even if one bit is 1, then result should be 1 then. But both LSB are 0, so output 0, then 0, 1, then we get 1, then 1, 0, again 1. And 1, 1, here there's a mistake here, it should be 1, 1. So please keep in mind that's a typing mistake from my side. Here it should be output should be 1, 1, 0, triple 1, 0. Now bitwise XOR. The output is 1 in XOR operation only if both bits are different. So let's compare each and every bit. LSB 0, 0. The bits are same, then output is 0. 1 and 0, 1 and 0. Bits are differing, hence the output should be 1. Again, 0, 1. Bits are differing, hence output should be 1. 1, 1. Bits are same, so output should be 0. Now this is bitwise XNOR, just opposite of XOR. Only when bits are matching, then output is 1. Then 0, 0, output 1, 1, 0, output 0, 1, 0, again output 0, and 1, 1, output is 1. So these were all the bitwise operators. Now let's take a look at the reduction operator. Reduction operators help us to reduce a multi-bit variable to a single bit variable. The various kind of reduction operators that are available in Verilog are reduction NAND, reduction OR, reduction NOR, reduction XOR, reduction XNOR. Now let's take a look at how all of these work exactly. And reduction operator. What will this do? We had the variable A, the value we assigned it earlier was 1101. Now, bitwise operator will take starting from MSB, then we will go till the LSB and perform AND operation with all the bits, cascading it from MSB to LSB. First of all, I perform 1 and 1, then output is 1, then 1 and 0, output is 0, then 0 and 1, then output is again 0, final output is 0. You can also generalize it if there's an AND operation, even if there is a single 0 in all the bits, then output has to be 0. As for AND operation, only when both bits are 1, then only output should be 1. You are going to try out in other examples as well. For any AND operation, reduction AND operation in a multi-bit variable, if there is even a single 0, then output will be 0. Now, reduction OR. Reduction, the same principle will be followed. Starting from MSB, we take OR with the next bit, then 1 or 1, then output is 1. 1 or 0, output is still 1. And 1 or 0, 1 or 1, output is still 1. Hence, final output is also 1. So, we can generalize it in this way. If there are at least one, there is a single bit that is high in a multi-bit variable, then its reduction or result has to be 1. Now, XOR. XOR is an interesting case. If you look at this question, we first of all take XOR with MSB and the next bit 1 XOR 1. Then output should be here 0. Then 0 XOR 0. What should be the output? The output will be 0 again. Now 0 XOR 1, then output will be 1. If you take a closer look at this pattern, when there are odd number of ones, then XOR will always give reduction XOR will always give output as 1. Now reduction NAND. Reduction NAND we can just take it as not of end result. So as the end result coming we had was 0, then not of 0 is 1. So reduction NAND will give us output 1. Similarly for NOR, we can just take not of the OR result. That is 1, hence the result will be 0. XNOR is just opposite of XOR, so the output will be zeros. So for as we said for XOR, reduction XOR, when there are odd number of ones in a multi-bit variable, then the reduction OR gives value of 1. For XNOR, the result is 1 when there are even numbers of 1. Now here the next operators are arithmetic and relational operators. These operators I feel we all have extensively used in one way or another. Simply, let's recall them. The plus operator, which is used to add two numbers. The subtraction operator is used to take difference of two numbers. The multiplication operator used to take product of two numbers. The division operator used to divide two operators. Now, the double star operator in Verilog is used to have the power operator. That A star star B means A raised to B. These are the arithmetic operator. Then modulus operator is also supported in Verilog. These are the relational operator, greater than equal to, less than, and less than equal to. Similar to the previous problem, let's try to see how will this work out. We have a plus b. Simply, the value of a is 10, value of b is 3. Then a plus b result should be 10. A minus b, 10 minus the result should be 7. A into b, that is 10 into 3, the result will be 30. A divided by 3, integer division, fraction part will be discarded. In Verilog, when there is fraction part via division operator, then the fraction part is discarded and only integer part is stored. So result should be 3. Now a raised to b, that is 10 raised to 3 should be 1000. A modulo b, that is 1. Remainder of 10 divided by 3 is 1. Is A greater than B? Yes, true. The result should be true. Is A greater than or equal to B? Still true. Is A less than B? 10 is less than B? No, that's false. So output is 0. And is A less than or equal to B? Still false. Because 10 is not less than or equal to 3. The result is false. So we have discussed these many operators. Let's again revise them quickly. First of all, we took a look at the logical operators. Then we take a look at bitwise operator. Then we discussed about reduction operator, and last but not the least, the arithmetic and relational operator. I hope you understood how these operators work. Now, the assignment for today is, as we have discussed about wires, and we also discussed about the logical operators. What I want you all to do is, I want you to make both NAND and NOR using AND gate or gate and NOT gate in Verilog. I will be providing a hint. You need to declare wires, and if you have some intermediate logic, you can use a wire to store that logic. For example, here I have assigned not of A is equal to not of A. Now for doing NAND, what I can do is I can just take the result of AND AB, then assign it to another wire, that is NAND underscore AB equal to not of AND AB. I hope that's clear. Let me repeat it once again. To make NAND gate, what I can do is I can take something like this, A and B, then I can put a not of operator in the result of AND AB and assign it to NAND. I want you all to try those. If you face any issue, please feel free to reach us in comment. There will be AND gate, OR gate, NOT gate, then NAND and NOR. These five logic gates I want you to try and model in Verilog. Just use a module, declare some wires, assign and end module. That's. I hope everything's clear. Thank you for watching.